Welcome to Pratidhwani, where we try to humanize science. I'm your host, GV Pawan Kumar. It is my delight and pleasure to introduce you to the guest on this particular episode, Joy Mitra. Joy is a professor at the School of Physics, Indian Institute of Science Education and Research, Thiruvananthapuram. And Joy has been an excellent condensed matter physicist who also is interested in topics at the interface of condensed matter and optics, including plasmonics, and has done some wonderful work over the years. And I know Joy for more than a decade now, because Joy also started roughly at the same time in IISER Thiruvananthapuram when I was starting here. And I've had a great interaction with him, learned a lot from his work, and also sat in our students' seminars and other things. So, Joy, welcome to Pratidhwani.
Thank you, Pawan, for inviting me to this great thing.
Yeah. So, Joy, we will get started with the origins of how you became interested in science. Give us a kind of a brief overview of your origins. Where were you born, and what was the kind of seed which took you to become a scientist?
Well, the origins. So I was born in Kolkata, Calcutta, as it was known back then. And I grew up in the city of Kolkata, so in a very urban environment. Yeah. I did my schooling in it's a pretty old school called St. James's School in Kolkata in the 1980s, primarily. 1990s, then I went to college to Presidency College in Kolkata, where I did my undergraduate education, BSc Physics Honors, and then went to Indian Institute of Science in Bangalore uh, to do my integrated PhD, which is a combined master's cum PhD program. So that's about the kind of academic origin, really. Yeah.
Wonderful. So you also have been kind of working at an area and a kind of an interface between condensed matter physics and also scanning tunneling microscopy and other areas. So were you always interested in this particular area of research, or did it take some kind of encouragement from somebody during your growing up times where physics was kind of strong aspect of your education?
Yeah, kind of growing up in kind of 80s Calcutta, I didn't have much idea even about the word condensed matter physics or anything as such. But tinkering was probably there around me. Yeah, at least what I very fondly recall, one of my grandfathers. Yeah, it was a joint family, so I had multiple grandfathers, and one of them was a radio physics graduate from the University of Calcutta. In fact, the first batch of radio physics graduates of the University of Calcutta. And so he was obviously my grandfather and retired by then. But 80s Calcutta, and many people of my age will recall, was filled with load shedding. So one of my earliest memories of tinkering around was to go to the nearest automobile, garage, the local corner garage, salvaging old lead acid batteries, half worn out, bring them home, changing some of the liquid, the acid, and then charging them and fitting them to small torch bulbs. Yeah, bought torch bulbs. Yeah, and creating small emergency labs. Yeah, so that's what probably my grandfather kind of taught me. Yeah, so you can call it tinkering, you can call it jugaad, you can call it whatever you want. But it at least gave me an idea that you can actually tinker with stuff all around you. Yeah, query stuff all around you, and yeah, I suppose that's what is tinkering, the whole idea of querying things around you. Yeah, and trying to mimic things around you. Yeah, that's what probably got me started, that you can do it yourself. Yeah.
Wonderful.
Yeah.
So you also mentioned that you grew up in a family which was kind of a joint family. So there were a lot of kids around your house also?
I'm a single child myself, but one of my uncles who used to stay with me, he had a son, so he was probably 2 years younger to me, and my playmate, and pretty much all throughout my growing up years, we kind of grew up together. not many more. We had a couple of other kids in the neighborhood, but we used to play around with occasionally. But yeah.
Wonderful, wonderful. So, one of the amazing aspect of the ecosystem in Calcutta is that the emphasis given to basic sciences, at least probably at the time 80s and 90s, there was kind of it was kind of an epicenter for education in basic sciences, including the presidency college where you graduated from. Can you give us a brief picture of that part of your education? How was it? Any good memories in terms of
Yeah,
education and beyond? Because
right.
college education is not just about only the classes.
Yeah, I mean, looking back, now that I stay in Trivandrum, looking back, uh, uh, it was a very strange place where I was actually born and the house I grew up in. Okay, so imagine a house which is one of the kind of not a main lane, but one of the by lanes of
Mm,
of
mm.
a old city thoroughfare. One of the by lanes. And believe me, if I got out from my house, okay, and I walked literally 50 meters to the left, okay, I would reach the place which was the birthplace of Satyajit Ray. Okay, it's
Wow.
an area called Gorpar. Okay, which if anybody have people have read the Felida series,
Mm,
yeah,
mm.
would instantly identify. Yeah, if I actually walk 50 meters ahead of me, yeah, straight, yeah, slightly more, probably less than 100 meters. Okay, I walk ahead. I would reach the house of Raja Ram Mohan Rai.
Man.
Okay, okay,
Okay, okay.
okay. If I reach 50 meters to the right of my house, I would reach the house of a man called Harinath De, who was one of the first Indian librarians of the National Library in Kolkata. And I don't know. I mean, he knew 22 languages.
Wow.
Okay, so it was a very strange place. Okay, it was a very strange place where I grew up. Okay,
Mm,
and this was bang opposite. If I walk 200 meters, I would reach the Raja Bajaj Science College, the Bose Institute.
mm, mm.
Okay, and all this I took for granted. You see, yeah, because
Mhm.
yeah. So therefore, and whatever came with it, there was small. So since it was bang very close to Bose Institute and Raja Bajaj Science College, obviously there were a couple of electronic shops around which kind of catered to the students of the radio physics department and the engineering departments of the Calcutta University. Yeah, there were a couple of small chemistry shops who used to sell test tubes, round bottom flasks, and stuff like that. Yeah, which were also kind of my neighborhood shops. Yeah. So even though I didn't have the exposure of the internet and the way we call exposure today, yeah,
Mm.
but I don't know how many people have kind of can grow up with chemistry shops and electronic shops as their corner shops. Yeah.
Nice. Yeah,
So
indeed.
yeah,
Yeah.
indeed, yeah. But and these are the shop owners, shopkeepers with whom kind of obviously I got pally. So I had by the time I was in class 5 or 6, I had an entire chemistry lab in my home. Okay, which were just hand out test tubes, hand out round bottom flask, hand out stuff stuff from these places, hand out magnets, hand out wound transformers, which are all given to me free because I used to go to the shops and rummage around. Yeah, so that helped, you see, very unknowingly. Yeah,
Mm, mm.
very unknowingly. The other very good memory, which is a completely contrast with what this and science, as one might say, is a memory that by class 8, people had little hope of where I would go. What to do in future. Nothing will happen. This guy goes on tinkering and making light bulbs. And in those days, there was nothing called a photocopying machine as these ones we see now. Yeah. So I was made an apprentice in a cyclostyle shop
Wow,
to
nice.
to, to learn
Mm.
to learn something so that I can earn my living in
Ah.
future. So, so there I went, to another shop where that guy taught me typing and
Mm,
cyclostyling for a couple of months, and I used to earn $5. Yeah, helping him cyclostyle other stuff.
mm.
Yeah, so
Wow.
very diverse kind of thing. Yeah, it was none of them were actually tailored to make me a scientist or
Mm,
take me anywhere, I suppose. But these are very fond memories, and I think all of them actually helped. Yeah, operating. I don't know how many people know how to operate a cyclostyling machine.
mm.
Yeah, so actually to make the plates and put in the powder and the yeah, I didn't even understand what I was putting in and what I was dusting, how I was shaking the plates. But all of that, I think, contributed to my later career. Yeah.
Wonderful. That probably would have also influenced you to go towards experimental physics. Had that a role to play, maybe?
Right, tinkering, yes.
Mm,
The thing
mm,
was that, all true-blooded Kolkata
mm.
Bengali science aspirants wants to be theoreticians.
Theoreticians. Yes, that's another thing. You're absolutely
Yeah,
right. I was about to
yeah,
actually ask that.
yeah, yeah. Yeah, yeah. So you all want to be theoreticians, and so did I. I also wanted to. When I landed up in IISc, I didn't have much idea of formal
Mm,
experiments, and the modern age research. Obviously, again, even from Presidency College, I didn't have much idea. So theoretical physics was something which attracted me. Till
mm.
I went to IISc and I saw the research labs. Yeah, and very gimmicky things like liquid nitrogen. I mean, we kind of play around with what kind of yeah. So a lot of so it was an eye opener that there
Mm.
is an institute like that within India, yeah, where had been admitted. So that was an eye opener, and probably during yeah, I kind of flipped towards experimental physics when I entered this lab where I did my PhD. I saw the scanning tunneling microscope, and
Mm.
that you could see atoms. Yeah, that's what I
Yes.
was told. That there is an instrument which could see atoms. TM still was not that common even in those days. Yeah, yeah, late 90s.
Yes. Yes.
But the STM and having access to it, and you can just see it on a bench hanging from a swing. Yeah, and that man sees atoms. You see, very
Mm.
very very attractive, very attractive. Yeah, that's probably and somehow I felt the fun guys were all in experiment in IISc physics in
Experiment.
those days.
True, true. So, how was your transition from presidency to IISc? You would have already got a good education in
Mhm,
presidency,
mhm.
and it was also kind of cultural change for you to go into IISc.
Yeah, I didn't have much clue about IISc. Nothing. I have had no clue about
Mm,
IISc
mm.
at all. Zilch, zero knowledge. I didn't know anybody of IISc. I was going to a new place, and I even remember on my train journey, we had to in those days we used to take the Coromandel Express down the
Mm.
east coast, the Coromandel coast, change
First, yes.
trains in Madras,
Madras.
yeah,
Yes, yes.
Chennai,
Chennai. You're right. You're
and
right.
and then take the next train to Bangalore.
Bangalore.
And I remember, I was traveling alone with a friend of mine from Presidency who had also been admitted. And I remember one of the very inquisitive co-passengers asking me that, so you have got a seat in some college in Bangalore. So I said yes. I said, so you could manage nothing in Kolkata. I said I didn't know how to answer. I said, so what's the capitation fee like? And, and that was the impression of people going down from Bengal to must have been you're not been able to do much in Bengal, and that's what you're kind of doing that. That was the impression. So same. I mean, I didn't have much idea about Bangalore at all. Never been to that city before. Never. Yeah. But IISc was pretty nice. I mean, the inside IISc, the campus was so beautiful, so beautiful, and obviously I went the first time I went was to give the interview. It
Mm.
was very peaceful, very peaceful at home, and the professors who were taking my the interview, IPhD integrated PhD interview, the entrance interview, they're very nice. They were very nice and very supportive, and I think I was very at ease in that place. It was very
Wonderful.
comforting.
Wonderful. So, also one of the most interesting programs in IISc, and which has also spread across even in other institutions, including IISERs, is the integrated PhD program. When it started, it was kind of a unique program because one takes in the undergraduate students at a level of BSc, and kind of almost mold them into researchers right at the age where they're trying to also get into streams of disciplines which they may not have much idea about, but they explore as they go along. uh, in fact, some of our best physicists, including you, have actually had this wonderful kind of training as an integrated PhD student. Would you also give a gist of how that program have really benefited you, and also the kind of uh, atmosphere it generates for students who are really at a level of undergraduate, who are now thrown into a totally research intensive program? And I've seen so many of very good researchers coming out of these programs, especially in physics, because that is something which I'm familiar with. Could you please give us a kind of an overview of that, Joy?
Yeah, it will obviously be my take on that story,
Yeah,
and
yeah,
I'm
yeah,
sure
sure.
the
Yeah.
other people will have their own take. But it was fantastic. Okay, that's only one word I have for it. It was fantastic. My experience was fantastic. See, first of all, it was in those days at least. It was absolutely unique by the fact that hardly any other master's level student. Yeah, so I had finished my bachelor's. Yeah, in Kolkata residency, and any other master's level student in the country would not get exposed to such facilities. Okay, be given that exposure, this sheer exposure. Remember, this is 97, 96, 97. Yeah, at the cusp of the internet becoming kind of opening up in India. Yeah, yeah. The iPhone was not there in the market. It
Mm.
is going to come in the future. Yeah, just to put it in context. Yeah,
Yes.
no smartphones. Yeah, hardly very few. Only the very rich probably had even mobile phones. Yeah, so you can imagine communication. Yeah, information transfer. Yeah. So in that backdrop, to suddenly it was even more important. Start that we were given that exposure. There were only a handful who are taken in every year. Yeah, typically 5 to 8. Yeah, students who are taken. Yeah, and obviously we had a free go of all the labs. We could practically go anywhere. Yeah, practically go anywhere. The NMR lab, to see an NMR
Mm.
machine, which you have just about heard of. Yeah, yeah. So that exposure and the freedom which that place afforded. Yeah, yeah, together with the courses and the curriculum and all that was there. But the freedom was immense. Yeah, yeah. I could actually, starting from the workshop
Mm. Mm.
to the most sophisticated instrument facilities, whatever we call the sophisticated instrument facility. Yeah, I could walk in anywhere. Yeah, I could walk in anywhere, observe practically anything. Yeah, and also probably since numbers were low, people were extremely, extremely tolerant of my intrusion, our intrusion. Yeah, we intruded on everything. Yeah, it was our playground. That was the confidence which was given to us. It's your playground. Make what you offer of it. Yeah, no, no, yeah, there's nothing really stopping us. So that kind of, I think, for all of us, in each of these integrated PhD batches, yeah, gave us a lot of confidence
Mm.
very
Mm.
early on, which is very important. It's not only information transfer is not the only purpose of education, Yeah, it is that instilling that confidence
Instant.
that you are capable. You are capable constantly. You are capable of understanding. You are capable of querying. You are capable. You are free to, query the system and understand, which was very different from I think that experiences anybody would have had anywhere in India. Okay, so which was an asset. It kind of gave us a lot of confidence that we could actually do it, and obviously being exposed throughout our masters thing to these areas of research obviously gave us a lot of time to kind of make up our minds at what we are interested in, where do our skills lie.
Mm. Mm.
Yeah,
Mm.
yeah. I was not having at gunpoint to choose a topic
Topic.
to start
Yes.
my career. Yeah, which was also brilliant. Yeah. And obviously
Wonderful.
there are fantastic people there, the academicians, yeah, with
Mm.
whom we could interact and learn from.
Wonderful. Wonderful. Uh, Give us a gist of the questions. What got interested you in your research problem? And of course, give us a gist of the lab in which you worked and with whom you worked and other aspects.
Yeah, so I worked with Professor Arup Rai Chaudhary for
Mm.
my PhD. Yeah, Okay, but at the point where I kind of formally entered, I finished my master's and kind of went on to my PhD. At that stage, he was appointed the director of NPL, the National Physical Lab,
Yes,
yeah, the
yes.
National Physical Lab in Delhi. So for the next couple of years, he used to come and go, yeah. But I had really fantastic seniors, yeah, and very fantastic seniors with whom I learned a lot. Okay, and the fun part of again Arup's lab was again akin to my childhood experience.
Mm.
We used to make a lot of things. There's a huge emphasis on instrumentation. So this scanning tunneling microscope, which fascinated me, was home built. Yeah,
Nice,
it was
nice.
completely home built. Okay, starting from the microscope itself, the only part of the microscope which was bought was the piezo tube. Yeah, the scanner tube. Yeah, that was the only part of the microscope which was
Mm,
bought. Yeah,
nice.
everything else was designed. Yeah, as far as the detection electronics went, yeah, for example, yeah, it was only the power amplifiers and the ICs which were bought. Yeah, having bought the ICs, the electronic circuit board was designed by seniors before me, improved upon by me. Yeah, and things. Only the computer was bought. Yeah, and many a times even the computer was self-assembled, if I use that word.
Yes, yes. That used to be a common practice
That
actually.
used to be a common practice. So you see, a lot of a lot of hands-on thing was going on there. Yeah, yeah, and that's what probably was very good as learning. Yeah, it was extremely. In terms of the research problem, as I told you, that you see, the first thing which fascinated me really and which got me attracted towards the STM, or the scanning probe microscopy, scanning tunneling microscopy, and the AFM, was this fact that you can actually image, quote unquote, image atoms or the atomic lattice in real space. Yeah, it was a fascinating idea. Okay, I remember, vaguely, I had been taught quantum mechanics at that stage, and I don't even fully understood what the meaning of this position of atoms on a lattice and things like that, and how do you visualize it? Yeah, but yeah, we had been taught that, for example, oriented pyrolytic graphite, or
Mm.
yeah, had a honeycomb lattice. Yeah, and that was the thing which was being told to me, that you can see that honeycomb.
Yeah.
You can see it. Yeah, you can image it. Yeah, real space. Yeah, yeah, and it is based on, and the imaging and the phenomena, and as far as scanning tunneling microscope goes, the physical phenomena which was being leveraged to do that imaging. Yeah, is quantum mechanical tunneling.
Mm.
Now, quantum mechanical tunneling is a bizarre phenomenon. Yeah, it's a bizarre phenomenon. Why it really mathematically fine, you get some solution. But once one starts thinking about the physical process of tunneling, yeah. So I think the attraction was pretty immediate and natural. Yeah, exactly
Absolutely.
those parts of the story or your education which you comprehend the least, and you are telling me there are actually tangible ways of latching onto it. Yeah.
That's fabulous. This is something a very important point what you mentioned, because traditionally physics education, the introduction of quantum mechanics is generally through a classroom lecture. Most of it actually is kind of through a framework where you will solve problems in a gradual increment of complexity.
Mm.
You'll start with a slightly more idealized solutions, then relax those things with approximations, and then add more complexity. But one of the questions, for example, tunneling is another great example what you just mentioned. You do learn and solve equations for infinite barrier, finite barrier, etc. problems, but to really understand that, one will have to have a physical system to look at it. In fact, people who really hypothesized, postulated, and extracted information were people who were aware of these questions. Now in that sense, it's quite remarkable, right? Because you have done something like a experimental quantum mechanics, so to speak.
That's right. That's
Yeah,
right.
yeah,
That's right. So it was no longer theory book, you see. That thing
yes.
was jumping out of the theory book, yeah, those books and those lectures, and it was staring at my face, yeah,
Mm,
and it was telling me you can do something useful with it, okay, and which was obviously by that time, I was going through my first year, second year,
mm,
yeah. Started. We had the integrated PhD program. There was a mandatory master's project,
mm.
yeah, which I did on scanning tunneling microscopy. And probably, yeah, by that stage, I was looking at those images, right, which my seniors were generating initially. and then trying to tinker around and play around with it. Yeah. Another aspect of I was always attracted to probably electronics. Okay.
Mm,
And
mm,
the circuit, the feedback circuit, which keeps the tip in position. Yeah.
mm,
Yeah. Between yeah, and which kind of stabilizes the tunneling in that instrument. Yeah. That feedback circuit is a fascinating circuit. It's what is known as a PID control circuit. Yeah, proportional integral differential circuit. Yeah. So you have learned integration, you have learned differentiation. What good has it given me all throughout? Yeah, it gave me marks, it gave me a certificate,
mm,
and you passed exams and so forth.
mm.
Yeah. But probably this was again the first time I was actually seeing a practical, a practical application of
Application.
an
Yeah.
integrator. Yeah,
Nice.
a practical application of a differentiator. Yeah. So it was many firsts, you see, of my theoretical knowledge, yeah, being applied in a practical sense, real time, and which was happening in front of me.
Beautiful. Wonderful. Wonderful. So, within this integrated PhD program, what was your broad learning in slightly broader context of not only just the physics, what you learned and also did, but how did also it open up your view on physics in general and science also in slightly more broader context? Because the transition is also very critical, and once worldview changes generally at that particular time, how did it influence Joy? Uh,
Yeah. So let me see. Okay, but it's a large question. A lot of things conflated
yeah,
together.
yeah,
But
yeah.
let's start with the physics first. Um, yeah. So a lot of good people thrown together at one place, right? Yeah, young people, integrated PhD students, PhD students, brilliant people,
Hmm,
all of them thrown together. Each one has their own interest. Yeah, and it's again an age which predates the internet or
hmm,
anything like that. Yeah, the biggest learning mechanism was by talking or talking to each other, discussing. Yeah, yeah. So I had people who were working on the sun. Yeah, so
hmm, hmm,
yeah. So the solar dynamo. I had seniors and peers who were working on condensed matter, hard matter system. Yeah. I had people who were working on NMR, nuclear magnetic resonance semiconductors. You see, there was a lab which used to grow, Professor Rachel Watt's lab, which used to grow crystals. Yeah.
crystals, yes.
So very diverse areas. Almost covering. There was a bioinformatics group, very very well established bioinformatics group. Yeah. So therefore, bioinformatics again was even unknown to me as a subject. Like, so
Hmm,
if you had asked me then that what is bioinformatics, yeah, and all this is happening under the umbrella called physics, the Department of Physics, Indian Institute of Science. Yeah. So therefore, the sheer diversity of the scope of physics. Yeah. Before that, physics was primarily what was the diversity of the textbooks. But these was practicing physicists, practicing researchers, scientists. Yeah. And especially the experimental those groups, they were actually having, they are designing things. Yeah. They are designing things. They are actually doing things. Yeah. So probably in terms of exposure, it was a kind of a big bang, sudden explosion.
hmm,
Yeah, for
hmm.
me. Yeah. So many different kinds of and those endless discussions and kind of, for us at least, that department was kind of home. Yeah, we used to spend more time in the department than in the hostel. Yeah, by any length of time. Yeah,
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 yeah.
yeah. So therefore, and the endless, you do your work. Obviously, you have your classes, you do your work, but then you do hang around, right? Yeah, and so we were hanging around in the department. Whoever was entertaining us in the first 2 years, yeah, and most of us were kind of voracious learners, I think. Yeah.
Hmm,
So we had an integrated PhD lab, which was supposed to be a lab. I mean, an official lab, but it was really our hang around place. Yeah.
hmm, hmm.
And again, I told you about my childhood that, where I used to go and scavenge things from shops, chemistry and physics stuff. Now we are scavenging things from the labs and making our own setups. That is our hang around
Nice.
for some of us at least. Yeah. The more tinkering types. Yeah,
Hmm.
and then going to these labs and doing these experiments and then, yeah. So that exposure and that crosstalk, okay,
Mm.
really influenced my worldview of physics. Yeah, really
Nice.
influenced my worldview of physics. It helped me. It uh, helped me understand that one could ask questions, but not only ask questions, but slowly, basically, what were the right questions to ask? Yeah, to frame the right questions. Yeah.
So
So that's
important.
about, yeah, right. So that's about, I think, my learning. The initial learning curve was that. Yeah.
Wonderful.
So that, yeah.
Excellent. Excellent. In fact, I'm very glad two specific points which you mentioned. One was that learning through discussion, that is such an important aspect, because a lot of learning, especially once you go a little advanced stage, happens beyond classroom,
Mm.
where you actually talk to your peers, and the language of your kind of communication uh, kind of really brings in new thoughts, because there are a lot of things which you are discussing with your peers, and you would be able to understand some things which might be otherwise only present in your head, and that externalization is a very, very powerful thing. And the second point you also mentioned is knowing the question. That is, I think, one of the biggest aspect as researchers we always have to really think about, and you very, very nicely kind of gave an overview of that particular point. So with this learning, you then moved from IISc to Belfast in
That's
Ireland, I
right.
suppose.
Yeah.
Yeah, tell us a little bit about that experience, Joy.
Well, yeah. So it's Northern Ireland, really, kind of politically
Yeah,
Northern Ireland.
Northern
The,
Ireland. I
the
have to
Irish,
mention that. I have to
the
be
Irish
specific. Yeah,
obviously say,
yeah.
Irish obviously say it is the island of Ireland. Yeah,
Ireland. Yeah, yeah.
beautiful place. I had zilch idea about
Mm.
Belfast, except for the songs, the Irish bands and the
Man,
songs, and yeah, which was I was a big fan of.
nice.
Yeah, yeah. So that was my only experience or any idea about Belfast. I didn't even probably know. I knew it was on the island of Ireland, but
Mm.
that's about the extent of where it was. So I was trained in, yeah, scanning tunneling microscopy. Yeah,
Mm.
I was very enamored by the technique. Yeah, okay. And rather than the material aspects or the physics of what I studied, I wanted to hang on to the technique. Yeah, I
Nice,
wanted to hang on
nice.
to the technique because that's what I had got. It had given me a lot of confidence, a lot
Like
of happiness, perhaps.
like a
Yeah.
pakka typical experimentalist, I
Yes,
should
yes,
mention.
yes.
Sorry to deviate, but this
No,
is a
no,
very
no.
important point, because that ability to really also go very close to the instrumentation aspect of it
Yeah,
is itself a very important thing. Yeah, please go ahead. Please go ahead.
yeah. So having kind of built myself two
Hmm.
STMs, one AFM, one low temperature thingy, I was married to that
Nice,
thing. Yes,
nice.
and therefore I wanted to kind of stick around. Yeah. So my PhD topic was on hard matter systems,
Hmm.
strongly
Hmm.
correlated manganites and so on. Yeah. So all the other what do you call postdoc offers that I got were on manganites, on strongly correlated systems, but not sticking to STM of that.
Hmm.
Okay.
Hmm.
But I wanted to stick to the STM aspect of it. And that's what I wanted. Okay, so this is the first opportunity which I got, and it basically told me that we will do that. It was an advertisement, obviously. It was an advertisement in one of these, I forgot now, but one of these online job
Hmm.
portals. Okay,
Hmm. Hmm.
jobs.ac.uk probably.
Hmm.
Yeah. And it basically said, tunneling induced light emission. Okay,
Hmm.
believe me, Pavan, that tunneling can induce light emission. I had no clue, in the sense
Wow.
of an STM.
STM.
Okay,
Yeah, yeah, absolutely.
yes, yes. Obviously, tunneling does induce light emission in the context of solid state system.
Solid state.
Yes,
Exactly.
yeah.
Yeah.
But
Yeah.
it caught me so off guard that why the hell didn't I think about it? That if it would happen in a solid state system, it could happen elsewhere. Yeah. But so tunneling induced light emission. Huh? So tunneling induced. So the word tunneling, obviously, this thing. So I went to look for the description of what that project was, and it basically told me that you see a tunneling electron, yeah,
Hmm.
a tunneling electron emits light. Okay, tunneling electron emits light from where? How? I spent some 5-10 minutes trying to kind of come to terms with myself that how, where. I actually got nowhere. Yeah. So I said, yes, I must apply for this. Okay. Okay. So I applied, and then in the next couple of days, I spent a huge amount of it. I was nearing my PhD, so I was writing my thesis, and probably doing a bit of odd jobs, and I tried to read up as much as I could. Yeah, about there was very little publication. Yeah, even in 2004. Yeah, on tunneling and light emission. But whatever I could, and obviously I knew the professor's name to whose group I was applying. So try to look up. Honestly, understood very little, and that's my first exposure to the word plasmonics. Also,
Nice.
yeah, yeah. So here was that there was no semiconductor, there was no band gap.
Yeah.
Nothing. Just two pieces of metal brought in tunneling contact, and I have been doing that, right, for the last 4 or 5 years.
Yeah.
Yeah, bringing various metals and various conductors in tunneling contact, and claiming to see atomic arrangement, etc. Doing electron spectroscopy, yeah, density of states, mapping density of states, so on and so forth. Never did I know that that can also give off light, yeah, and that too from two metals.
Wow.
So obviously it got me intrigued. It was the perfect way to kind of poke me. Yeah, this is something which you don't know. Yeah, throw that on my face. So then it we applied, and they kind of shortlisted me, wanted an interview in which I claimed I have no clue about the topic, but I know about the STM. Okay. So they told me, okay, so you have never heard of this? I said, no, I have no clue what this is about. Yeah, but I am confident about the STM. So it says that we are setting up this new thing, and we will probably give you a commercial STM. Will you be able to set it up and get it going? I said, yeah, I'll do it. I do it. I had never seen a commercial STM in my life. Okay, I had no clue about what a commercial UAG STM looks like, but I absolutely super confidently promised it. And they selected me. I was kind of very happy because it was STM, and it was an area which nobody else, I had zero exposure about. Yeah. And it was a completely new thing which I'll be learning. Yeah. A new adventure, you see. It was a new adventure for me. Maybe a bit naive, but it was an adventure. So that's
Nice.
what took me to Belfast, the Queen's University, where I stayed on for the next 6 years.
Very nice. Cool. So, overall, how was your experience there in terms of culture and other things? You would have probably also learned a lot of things beyond, again, science, right? There
Oh,
again.
yes. It was a fascinating place. It was 2004, 6 years, just 6 years beyond the Good Friday Agreement. Yeah.
Wow.
Yeah. Okay. And it was a Northern Ireland in change. It was a Northern Ireland in change, and it has changed. Yeah. So non-physics stuff, what I learned is that I learned about experiments in making what should I say, an international, not vanishing an international border, but it was an experiment in making a border irrelevant.
Nice. Beautifully put.
Okay. It was an experiment. It has had its ups and downs. I have not always followed, but it fascinated me that people dare to dream to make a border irrelevant.
Yeah. Excellent. It's so nice to actually hear that in this day and age, where and also on the on the day when we are recording, it's something which
Yes,
is very important.
yes.
We are recording, by the way, on 15th August. I have to
It was on
mention
15th
this.
of August. Yes,
Yeah.
yes, yes.
Which is Indian Independence Day for people who are just not aware of. So Joy, you then made a move back to India. First thing is, why did you move back? And what you always, because I am very sure for the kind of work you are doing, which is very exciting and interesting, you would have also stayed back in the
Yeah,
West. Yeah.
yes. Probably that would have been. But honestly, Pawan, I had to move back to India. Okay. It that I don't know who made that plan, or who. It's not that I consciously made that plan that I will come back to India, and I don't know. I mean, as I said, it was an adventure for me. Yeah.
Nice.
But what was there was that I had to come back to this country. Yeah. That was always a done deal. It's only a question of time. It was only a question of, learning and getting the right place, the right thing. Yeah. Had I not got a job of the kind which I am at today, what
Mm,
I would have done is probably a very different question.
mm,
Yeah.
mm.
I don't think I would speculate that far.
Yeah.
But but it was always a thing that I had to come back and I had to stay in academics. Yeah. That probably was a kind of a growing up dream. Yeah. Which yeah. So yeah, I mean, when people started telling me kind of about all my over the years, I was making trips back to various places in India,
Mm,
giving talks, etc. And people were trying to tell me by 2008-9 that I think you spend a couple of years now, you start applying, yeah, start thinking about it seriously. Even people from IISc and
mm.
JNC, various people trying to tell me that, and that's when I got into the thing of taking the application seriously, and and IISER Thiruvananthapuram was set up in 2008. Yeah,
Mm.
2008, and and one of these trips um, I met a couple of people there, and people guided me that why don't you apply there? Yeah, it's an upcoming place, lots to do. Yeah. So that's how it happened. I applied and I got the job. And in 2010, I shifted back from Belfast to Trivandrum.
Very nice. Very nice. Uh, kind of give a just as of the kind of questions you have been asking in your research group now currently,
Right.
and also some of the things what you've been doing there. And
So obviously, my research after going to starting from my postdoc has been on tunneling induced light emission. That took a was a prime focus of my research. The tricks which I picked up or during my postdoc years, and so I established myself more at pairing the surfaces and interfaces in
mm,
general, right?
mm,
And they are the kind of hotspot of anything, much of the interesting physics that goes on. Yeah. So probably I would say that so I came back to India, and we continued in scanning probe microscopy in my lab. We have continued. Yeah. By that time, asking the question of light emission. So the fundamental physics aspects of why does light come out of tunneling, an electron tunneling from one metal to the other? Yeah. By the way, it's not fully understood yet.
mm, mm.
But that was one open question, and which we kind of drove me out in the background. Yeah. That the phenomena of light emission, yeah, from the tunneling, yeah. But we obviously, once you come back to India, and you start establishing a lab, you take PhD students, yeah, you just don't survive on such questions, yeah. So there were various other projects which kind of took off, but all under the theme of pairing interfacial physics. Yeah, interfacial physics. So there are a couple of things which got me interested, and one was that detection, for example, of hydrogen. Yeah.
Mm,
By palladium, which was a very well established mechanism. Yeah. And what was very interesting was that we were doing some work, and we realized that instead of a very thick film of palladium, and you try to detect hydrogen, yeah, you make a very thin film, a very granular film, a bad film.
mm.
Yeah, somehow, yeah, miraculously, its sensitivity to hydrogen is even much higher, yeah, than a very thick film of palladium. Yeah,
Palladium. Nice.
yeah,
Nice.
yeah,
Very
yeah.
interesting. Mm,
And why? Because you see, the granular film again has a lot of interfaces.
mm,
Yeah.
mm.
And much of the action of the change of resistance or whatever the innards of that detection mechanism, yeah, once you make it the films very granular, yeah, the sensitivity to this external agency, in this case hydrogen, yeah, was extremely sharper. Now you look at it that it's a much bigger phenomena. For example, when you do light detection, yeah, you want to detect light. Yes, there are materials whose resistance changes when you shine light on. Yeah, the conductivity changes, so on and so forth. But much of the interesting devices which actually do light detection, yeah, they are all junctions. They are all junctions. For the
Very
photo
interesting.
detectors are all junctions. Okay. So you see again, when the moment you have a junction, and if you kind of just hark back maybe 100, slightly more, 100 more than a bit, 100 more years, if you look at J.C. Bose's patent, I don't know if you have
Yes,
ever come
yes.
across that.
I've heard,
Yeah,
yeah. I mean,
yeah,
I've read and also
yeah,
seen some
yes.
something.
If
Nice.
you, if you look at the patent application, yeah, this is late 19th century, yeah, you see, and where he kind of has this a block which he calls galena. Okay,
Yes,
yeah,
yes.
well, yeah, this predates quantum mechanics. It predates electrons. It predates all. Yeah, a block of material called galena, and he has a whisker, yeah, which is kind of plunged into it. Yeah, that's a metal semiconductor junction. You see, yeah,
Wonderful.
and then and he draws an eyeball like structure, and says radiation can come and I can detect radio waves. That's his detector. Yeah. So 100 years hence, I mean, you see, we were still kind of looking at junctions. Yeah, and we were still looking at junctions, and so that is something, this interfacial property, junction property, and the range of physics which is enabled by this thing called junction. Yeah, always fascinated me. Yeah, whether be it chemical detection, whether it be kind of light emission, whether it be light detection, so on and so forth. Yeah. Huh. So if I want to put it under an umbrella, I have probably over the last decade or so done various kinds of experiments. Yeah, and in each time I have seen, knowingly or unknowingly, I have gone back to a junction and the physics of a junction. Yeah, it can be a metal semiconductor junction. Has been a metal metal junction. It has been a semiconductor semiconductor junction. Yeah, and
Wonderful.
yeah,
Kind of an overall theme has been physics at junctions, right?
that's right. Yes, 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 yes.
Kind of also in this particular case, it can be nano junctions, so to speak.
Yes,
Yeah,
yes, yes, obviously.
and that's so. This kind of theme also, one of the things what I have also read and seen from your group is this unique material called as epsilon-near-zero kind of materials, fabulous optics, and also in that way you've been able to really bring together condensed matter physics, this junction physics, and also optics on kind of one platform. Can you give a very brief gist of that problem, what your group is also looking
Right.
at? Yeah.
Right. So these epsilon-near-zero systems, yeah, it's a fascinating material. Yeah, it's
Uh-huh.
very common material. Everybody has it on their mobile phones. The screen
Yes.
of their mobile phones, indium tin oxide, one example. Yeah. You see, I think it's the way I was taught optics, which is what kind of got me interested. Refractive index is one, yeah, which is the refractive index of vacuum or free space, yeah, and every other material that one has, this thing come across, in which light propagates, has a refractive index higher than one.
One.
That is a
Yes.
kind of accepted knowledge. Yeah, that is what I was taught, and believed it. Yeah, obviously I came across meta materials.
Mm.
Yeah, down the research of plasmonics. Yeah, but which were artificially constructed materials where one could kind of effectively have an epsilon or a mu deviating from the standard
Standard.
value. Yeah. Okay. And obviously, we also, you'll appreciate, we knew about the Drude model. How do you
Mm.
model
Mm.
these kind of, yeah. So all this is known. Yeah. Now you suddenly have, what about the epsilon-near-zero? So the thing about epsilon-near-zero is that the real part of the dielectric function of a material, yeah, yeah, remember the dielectric function comes from the polarizability.
Polarizability.
Yeah, even
Yes.
the linear part. Huh? Even if you take linear polarizability, it comes from the polarizability, and the dielectric function obviously is a positive value for most dielectrics, and it goes less than zero, in metals. Yeah, that is
Mm.
the standard knowledge. Yeah, the standard knowledge. Drude's model kind of shows you that. Nobody really kind of primes you for the range where it actually does the zero crossing. Yeah.
Mm. Mm.
So if it does the zero crossing, so it obviously varies with energy or wavelength. Yeah, that is known to us. And so very, very serendipitously, I was trying to, again, very theoretically, I was
Mm.
trying to analyze certain aspects of the Drude model, and trying to see what happens when it goes closer and closer to zero. And then obviously metamaterials were there. And then I started wondering that are there real homogeneous systems, yeah, bulk homogeneous systems, which actually do this.
Mm.
Okay,
Mm.
because the Drude model was telling that anything which follows it would be doing this at some stage. Yeah, yeah, and then obviously in gold, in these metals, there is obviously this ultraviolet transparency,
Nice.
but that is again not something which is very common. It's deep. It's kind of into the ultraviolet. Not a lot of experiments are done there. Yeah, so we know theoretically, yes, and experimentally it happens, kind of. But then, as I was kind of probing it a bit further, then one came to these doped semiconductors. Yeah? Doped semiconductors, which have a Drude-like model for conductivity. Yeah. At the same time, they are transparent. Yeah. So high conductivity and transparency doesn't really go hand in hand. Yeah.
Mm.
So none of the metals are transparent. Yeah. Yeah. Uh, and then slowly it was this material called indium tin oxide, yeah, which is on all mobile
All
phones,
my, yeah, yeah.
yeah, all over the place, and which is transparent yet conducting. Yeah, how the hell does that happen? Huh? So yeah, the moment you have a large electron density, it tends to become opaque. It does not let light through. Yeah. So it was a mixture of this theoretical understanding and having realized that you have this material indium tin oxide on your table, and which does this. Okay, slowly got us working in this area. Yeah, got us in this area, and then you slowly start asking the question that so where does the conductivity actually come from? Where is it transparent? Is it transparent over all wavelength ranges?
Mm.
And the answer is obviously no. Yeah, it is a metal. It is a metal. It has a metal-like optical behavior, and at very long wavelengths, it does start behaving like a metal.
Metal. Mm.
Yeah, but at low wavelengths, which is essentially the visible wavelength, yeah, somewhere from 400 to 700, yeah, it is transparent. It allows light through, and so therefore epsilon is positive, and at longer wavelengths beyond, let's say, 1200, 1300 nanometers, it behaves optically more like a metal.
Metal,
Yeah,
yeah.
and has the characteristics of a metal. It becomes highly reflective. It is not at all transparent there. Yeah, and then you obviously again you kind of set up your lab to query the right.
Mm.
IR optics is not a very easy thing to do. It's not the same as equivalent as visible optics in terms of components, detectors, etc. So
Yeah.
it took me a couple of initially 2-3 years to get the right items together, write a project, to buy the right detectors, the optics, etc., etc. And that's what really got us started. And this thing, and it's absolutely fascinating. It's a homogeneous material. It's not a metamaterial. It's a homogeneous material, and there is a small window, just before the zero crossing, which is
Mm.
probably the most interesting area. And the interesting area is that in this very small window of 100 to 200 nanometers, just before the zero crossing, before the epsilon, where epsilon goes to zero, yeah, in that wavelength range, the refractive index is less than 1, and the permittivity is still positive,
Nice.
which
Nice.
means that there are propagating solutions of Maxwell's equation, the wave equation, yeah, the corresponding wave equation. Yeah, it's not a decaying solution. Yeah, it is a propagating solution. Yet you have refractive index less than 1. Yeah, and that has been really fun. Again, very rewarding. Trying to now understand propagation of modes. Yeah, what
Mm.
kind of
Mm.
modes can be excited? What happens to the wavelength of light when it try to propagate a mode in that regime? Yeah, so it has been
Nice.
quite interesting couple of last 4 5 years now. Yeah, for me, again, a learning curve. Yeah,
Ah, yeah. It's always a process. That's actually the beauty about our kind of
yes,
occupation,
yes, it is.
because the learning never stops. In fact, it
It
just
never stops.
gradually
It
never
never
stops.
stops. It
Absolutely.
never stops. Yeah.
Fabulous, Joy. This has been a pleasure. Before we kind of end, I also want to touch upon some things which is very, very interesting. You have been also an excellent mentor. not only to PhD students, but also many undergraduate students, and in all official and in an unofficial capacity. I've also met some of your students in some conference where they tell they would have done some masters or even a PhD with you. And tell us a little bit about that experience, because IISERs generally have a very large student population which is interested in science, physics especially, and you have been a very active mentor in your institution. I just want to get a gist of that part.
Oh, it has absolutely been fascinating. It has
Nice.
absolutely been fascinating. I don't think, obviously research has been very rewarding, but if anything has rewarded me equally, it has been interacting with the students. Yeah. Believe me, teaching a first year class,
Yeah.
especially things like electromagnetism, and then electrodynamics. Yeah. And their eyes light up, Pawan.
Light up.
Yeah, I'm
Yeah.
sure you have experieed the same
Yeah,
thing.
absolutely.
Yeah.
Absolutely.
And that you see it's I mean mm, that kind of makes a bond between you and your
Yeah,
students, kind of, because you're kind of,
absolutely.
yeah, you had the opportunity, the pleasure, the honor of showing them that first way. Yeah, it's absolutely fascinating, and it's so rewarding, so rewarding. Yeah, because they carry it through their lives.
In
Yeah,
lives,
i
exactly.
carry it i carry it through my life. Yeah.
Beautifully
So,
put it.
yeah, and therefore that has been absolutely fascinating. And even today, I mean, unfortunately, what happens is when we, from our career, which will happen
Hmm.
to you also, uh, the age difference between the first year class and us goes on
Kyogosan is
increasing.
decreasing
Yeah, goes on increasing
monotonically with every batch.
with every batch.
Yeah.
Okay, but again, maybe I am kind of kind of deluded or naive. Uh, the association with them, I think, kind of keeps me also young
Yeah,
and
yeah,
grounded.
absolutely.
Okay,
Absolutely. Yeah.
both things happen. Yeah, both things happen. They don't shy off at asking any questions. So,
Yes.
yeah,
Yeah.
okay, and therefore it keeps you grounded. Yeah,
Grounded.
it again
Absolutely.
takes you back to the drawing board. Yeah,
Drawing.
time and again it has happened to me. Yeah, and querying my understanding of aspects of it.
Beautifully put. In fact, it also kind of reminds me of many physicists who actually have talked about how important teaching is. For example, Feynman actually emphasizes that. And there's also been a lot of discussion telling that in the longer run, it is the exposition of the scientist, which also has equally important kind of bearing on the knowledge, as much as, let's say, the research papers what we write and do things. um, yeah, it's been a fabulous kind of conversation, Joy. As
Yeah,
always, a great learning process, and I am very sure you also have some interesting directions to take. I also know that you are working on some 2D material research
that's
and other
right.
things.
Yes, yes.
So,
With
is there any specific area you are also now exploring, taking this
um,
part of it?
yeah. So what I've recently started working on is again another kind of a fascinating thing, which is basically strain engineering in
Hmm.
2D material systems.
Materials.
Yeah.
Yeah.
So it's not it's not uniformly straining material system by stretching or bending. Yeah, but it's more like methodically, but still random
Hmm.
straining these 2D sheets by putting them on patterned substrates.
Nice. It's
Okay,
nice. Nice.
pattern substrate. So the patterning can be two way. Either you can have a pattern
Hmm.
sticking
Hmm.
out of the substrate, or you can have holes kind of dug
Also, yeah.
into the substrate. Okay, and you transfer these 2D material systems, and lo and behold, just like as you would expect a tablecloth or a trampoline sheet or something like that, yeah, to paint a picture.
Hmm. Hmm.
Yeah, so it kind of more or less these they're such fascinating materials, these 2D stuff.
Nice.
Yeah,
Yes.
they almost conformally drape and create wrinkles. Fantastic stuff, man. Yeah, and it has been absolutely fun modeling them, modeling these wrinkles and
Hmm.
patterns which are formed, and then understanding that how it changes the band structure of the system. The
System.
material band structure, yeah, is thoroughly changed. Yeah, once you have these strains and wrinkles, yeah, it affects every possible add-on property that one would be interested in: the local dielectric function, the local mobility
Yeah, that's very fabulous. So in that sense, you would be able to now modulate the mobility by engineering the underneath surface. That's what you're
That's
saying.
right. But do remember, I mean, mobility is a kind of average value theoretically, at least.
Yeah,
Yeah.
yeah,
But
yeah.
here we are kind of speaking of local mobility
Local
because you're
mobilities. Yeah,
locally straining it. Yeah. So it's a,
yeah.
yeah. Yeah. So it's some kind of an, yeah, if you want to really speak of mobility, some kind of an average thingy, but it is really speaking of the local interaction in that region. Yeah. How does the mobility change? How does the dielectric function change? Which are no longer homogeneous across the entire 2D flake
2D play.
at all.
Nice.
Yeah, but that has its advantages. Yeah, in what they call funneling excitons and stuff like that. Funny stuffs. Yeah, but it has been fun learning about strain, which is a very mechanical thing,
Mechanical thing. Yeah, yeah.
elasticity kind of thing, very different from what I'm used to
Mm.
in terms of electronics and optoelectronics. Yeah.
So do you have plans to also strain it using tip?
Yes, yes,
Yeah,
I've tried
yeah,
that, but also kind of my focus has been that okay, so even if you can do them, it'll be kind of lab curiosities.
yeah,
Yeah.
yeah,
To
yeah.
do something to do something which is actually kind of makes sense, yeah,
Mm, mm.
on a slightly larger scale, I'll have to engineer them in some other way.
You're right. You're right. Yeah, because that's the actual important aspect of 2D material because it's actually spreads across a larger
That's
area and
that's right. Right. So yes,
fabulous.
as you said, with the tip, I'll be able to, and if I put it on a
Mm.
hole and kind of, I'll be able to do that. Yeah. And there is a lot of interesting physics there, which is a slightly different story in terms of vibrational modes, etc.,
Mm, mm.
etc. Yeah. But as far as the strain engineering in terms of electronics goes, yeah, that is too local and too localized. If I do it by the tip, it will just remain too local. Yeah, for it to be useful on any large
Useful.
scale. Yeah.
Fabulous, fabulous. So I wish you and your research group all the best in
Thank
all
you,
the
Pawan, and thank you for inviting
ventures.
me here. It's brilliant.
Yeah,
Yeah.
my pleasure. So this is Pratidwani, where we try to humanize science. This time with the one and the only Joy Mitra. Thank you, Joy.
Thank you, Pawan.